First of all, let me express my gratitude to my colleague and good friend Said Ahmed Edelat Panna for his initiative in creating the International Society of Fuzzy Sets Extensions and Applications and the consequent holding of this first international conference of that society. Thank you very much also, dear friend, for your kind invitation to participate in this conference as a keynote speaker. Well, as you know, mathematical optimization is present in a large variety of human activities, ranging from finding the fastest route to work or looking for the best house given certain budget constraints, to solving complicated problems in economics, engineering, industry, medical sciences, not to mention its important presence in artificial intelligence, AI, in the sequel. Given the omnipresence, importance, and vitality that AI has today, I will dedicate my today's talk to shed some light on how to obtain optimal solutions in optimization problems when this task has to be done in an automated way, i.e. by an automated decision-making (ADM) system. To describe how to model the decision-making process so that ADMs work as correctly as possible and particularly improving the way to obtain optimal solutions from humans. As you all know, there are dozens of definitions of AI, each and every one with pros and cons, so that unlike the concept of algorithm, which is unique, the same cannot be said of AI. To avoid this drawback, the European Union has decided to set aside the problem of defining AI to concentrate on what is an AI-enabled system which, in a roundabout way, unambiguously characterizes AI as it appears in this slide. As a whole, the study of the AI includes several approaches and techniques, such as machine learning, of which deep learning and reinforcement learning are specific examples, machine reasoning, which includes planning, scheduling, knowledge representation and reasoning, search and optimization, and robotics, which includes control, perception, sensors, and actuators, as well as the integration of all other techniques into cyber-physical systems. Systems with AI, as mentioned in this definition, are usually called automated decision-making (ADM) systems, which is a term that is beginning to be used as a substitute for AI because, on the one hand, it is less imprecise than the latter, favoring that people are more comfortable talking about ADM systems than AI, and on the other hand, because in general, automated actions are understood to be actions designed and programmed by people to be performed automatically. It is therefore evident the prominence that decision-making and optimization have in the context of artificial intelligence, justifying that in what follows we will focus on explaining in detail what a decision problem is and particularly what a decision-making problem in fuzzy environment is. Classically, the approach of a decision problem requires knowing the following essential elements. One decision maker, which can be an individual or a group. A set of actions on which the decision maker can choose. A set, called the environment, which is constituted by the situations, states, that the decision maker can encounter when choosing and cannot control. A set of consequences associated with each action and each state. A criterion that orders the consequences. The nature of the information available. The duration of the process, and the social framework in which the decision-making process takes place. Thus, if we assume in all that follows, A, an individual decision-maker, that is, we do not consider group decision-making, GDM, problems, B, a single management criterion, thus avoiding the multi-criteria decision-making, MCDM, problems, and C, the duration of the process is limited to one stage, so as not to enter into problems typical from control theory. A decision problem is described by a sextet, X, I, E, C less than or equal to K that includes the set X of possible actions for the decision maker, the available information I, the environment E, the set C of the consequences of actions, the criterion less than or equal to that orders the consequences, and the framework K, which is the framework in which the decision maker decides. It is well known that under very mild conditions, an optimization problem is nothing more than a particular case of a decision problem. This assumes that to solve an optimization problem, first, a model that includes and leaves out certain features of the real world should be defined. This model is composed of three basic elements: decision variables, a set that restricts the values taken by the decision variables, and an objective function that measures how good a solution to the problem is. The goal is to select an optimal solution, in the sense that it maximizes or minimizes the objective function from the set of all feasible ones. However, what is usually omitted in the model definition is the fact that people do not make decisions in a vacuum or in isolation from the reality that surrounds them and the specific problems they are trying to solve, namely, that there is always a decision-making framework, hereafter framework for short, that dictates which decisions should be made and how to make them. Therefore, ignoring the framework in the modeling or solving stages of an optimization problem almost surely would lead to an optimal but useless solution and, consequently, an unacceptable decision. In this regard, it is worth noting that when faced with the same problem, each person could make a different decision, choose a different solution. This is because each person has their own framework determined by their experiences and the specific situation in which decisions must be made, and, consequently, what is called an optimal, best, solution may lose this quality when it is analyzed from the perspectives of different frameworks. Clearly, the idea of best is framework dependent. For our purposes, here we adopt the idea that framework consists of a set of features of the environment surrounding generic activities, and that these features can be encoded and made available to a software system alongside an encoding of the activity itself. But we do not know how to model frameworks nor what general operational ways of using frameworks there are to solve optimization problems. So, in what follows, we will address the next two essential questions. How can the framework be formally modeled? How to obtain solutions to optimization problems that conform to a given framework? Some basic definitions from fuzzy logic constitute the theoretical basis to model the frameworks. Particularly important are the definition of fuzzy set, linguistic variable, fuzzy proposition, aggregation operator, T-norm, T-norm, negation, or fuzzy implication. Some commonly used definitions of the logical connectives are shown in the table in the slide. Let it noted that in the case of implications, not all of them satisfy the conditions imposed in the definition of fuzzy implication. Nevertheless, they are used as such in the literature. Fuzzy propositions can be classified into the following types: unconditional and unqualified propositions, unconditional and qualified propositions, conditional and unqualified propositions, conditional and qualified propositions. Fuzzy propositions can be combined by using the logical connectives and, or, not and implies to generate compound propositions. Thus, we may have propositions like these one shown in the slide. The concept of framework is generic and depends on each specific research field. Here, we consider it as a set of rules that establish the qualitative characteristics that the available decisions must have. Then, we propose two approaches to solve optimization problems posed within frameworks. The first is an a priori approach, in which the framework is explicitly included in the mathematical model of the problem. The second is an a posteriori approach, in which the suitability to the framework of some previously calculated solutions to the problem are checked by using a multi-criteria decision-making methodology. Thus, a framework F in a fuzzy environment could be expressed as the set of fuzzy propositions shown in the slide. The choice of logical connectives depends on the specific situation and should provide the best description of the decision-maker's reasoning with uncertainty. There are experimental and theoretical, choosing according to some reasonable properties, methods to do it, but the problem of choice remains. The general mathematical programming problem, considering a fuzzy framework, can be formulated as it appears in the slide, where x is a real-valued vector, f is a real-valued function, and g and h are vectors of real-valued functions with adequate dimensions in all cases. Lastly, x belonging to f means that x makes the propositions in f true at least to a certain degree. Clearly, all propositions in f must be related to x in some way. In the a priori approach, and according to the definition of framework, a solution to the problem 1 must have the qualitative characteristics established by f. This means that all propositions in f must be satisfied. We see this requirement as the conjunction of all propositions in f. Consequently, by using a suitable t-norm aggregation operator, the problem 1 is transformed into this crisp mathematical programming problem 2, where alpha is an auxiliary variable and m is a very large constant. The product alpha by m penalizes the solutions that do not satisfy the framework. On the other hand, in the a posteriori approach, depending on the number of propositions in f, but mainly on the choice of operators that model the logical connectives and the membership functions used, the problem 2 can be difficult to solve due to possible discontinuities, nonlinearities, and non-convexities that can be introduced in the problem model, and then an alternative approach is to obtain a set of good, feasible solutions to the problem 3 by using exact algorithms, simulation, or meta-heuristics and analyze their suitability according to f. In fact, it may be the case that problem 3 has a special mathematical structure for which efficient solution algorithms exist, and this structure may be lost if additional, framework-related, constraints are included. This approach results in a multi-criteria decision-making problem. Going back to the beginning of the talk, I will not insist on the importance of optimization problems in the design and development of automated decision-making (ADM) systems, but I will show the next step we want to take in order to solve real decision-making and optimization problems with artificial intelligence techniques. Within the multiple perspectives from which ADM can be studied, we want to address the operational point of view based on the premise that the study, understanding, and adequate treatment of the underlying optimization and decision models in ADM are indispensable conditions for the satisfactory resolution of the problems they address. These aspects have been already studied in some previous projects developed in my research group, and hence, based on the results obtained, the lessons learned, and as a continuation of the aforementioned projects, it is natural to consider that automated decision-making can be positively enhanced by having several independent ADMs that solve the same problem, but using different decision models, integrated into an automated cooperative decision system, CADM, to obtain a decision that takes into account as many aspects of the original problem as possible. In short, and as it's shown in the scheme of this slide, The next step will be to study and propose operational models of automated cooperative decision systems, CADM, that allow to enhance decision-making by being based on multiple criteria and data that are not simultaneously available in individual ADMs. The leading role of decision-making in everything related to ADM is beyond any doubt. But despite the wide range of fields and applications in which ADM can be applied, certainly with excellent performance, there are still quite a few activities in which human beings perform better than ADM. Among these activities are creativity, empathy and emotional intelligence, critical thinking, interpersonal communication, complex decision-making, leadership, teamwork, moral awareness, or adaptation to change. It is evident that each and every one of these activities has clear fuzzy connotations, which demonstrates the validity and potential of fuzzy sets and systems to improve the performance of ADM, making it absolutely necessary to continue deepening the study and research in this area of science, which precisely this year 2025 is 60 years since the first publication on the subject appeared, authored by our always well-remembered Professor Lotfi Zadeh. Thank you very much for your kind attention.